Hey everyone, today we're going to be talking about partial reactions and mixtures of gases. So first of all, what do we mean when we say partial reactions? Well, for the past few weeks in LPSA, we've been talking about reactions that go to completion. In other words, we calculate the limiting reactant, we make it go to zero, and then we calculate the corresponding products and the other reactants if there are any concentration or moles amount. Well, that's not always what happens in the real world. Consider this cup of water here. It's clear, right? But as soon as we add a little bit of salt, we swirl it around a little bit, and it all dissolves, correct? But then what happens when we add even more salt? Well, if you take a look at this cup of here, there's a lot more salt that's undissolved. But what's actually going on here? So in this case, we can say that the reaction has reached equilibrium. Equilibrium is a fancy way of saying that the rate of the forward reaction has equaled the rate of the reverse reaction. That still sounds a little bit convoluted, I know. So we can simplify that. When we expose salt into water, what happens is that the salt ions, Na plus and Cl minus, dissociate. But what's also going on in the background is that the ions, Na plus and Cl minus, come together to reassociate into the NaCl. And so basically, this is what happens in a lot of real world situations. And so we can't really use what we've been learning in LPSA to just calculate the limiting reactant and go from there. Instead, we have to use a different method. And what we just talked about here, the reaction between liquid and solids, can also be applied to the relationship between gases by themselves. And so here, we have a nice little problem from problem set 3. A steel vessel is filled with 0.4 atmospheres of CS2 gas and 0.6 atmospheres of O2 gas, that's important, at 298 Kelvin. The mixture of gases partially reacts according to the following reaction. At the end of the reaction, the total pressure inside the vessel is 0.85 atmospheres. Cool. And they want us to calculate the mole fraction of each gas at the end of the reaction. Excellent. So what do we have here? We have 0.4 atmospheres, 0.6 atmospheres, and then we have 0 and 0. And instead of calculating the limiting reactant, which we don't know again because we don't know what value makes this go into equilibrium, we use this variable x. Let x be the amount of gas reacted in atmospheres. Cool. So we start here with x times 1 for the corresponding coefficient, minus x times 3 for the corresponding coefficient, plus x times 1 for the corresponding coefficient, plus x times 2 for the corresponding coefficient. And at the end of the day, we have 0.4 minus x, 0.6 minus 3x, and then we have x, then we have 2x. And now, to calculate the mole fraction, we need to figure out what x is equal to, right? And then we have this added additional piece of information that the total amount of pressure at the end of the vessel is 0.85 atmospheres. Cool. So then we can just add the total amount of gas at the end together from both the reactants and the product side. And when we solve this equation, we get the solution that x is equal to 0.15 atmospheres. Excellent. But then how do we go to getting the mole fraction? Well, we learned that the mole fraction of the gas is equal to the partial pressure of said gas for partial pressure of the total amount of gas. So for CS2, we can go ahead with the assumption that 0.4 minus 0.15, which is the x value, and again, we're just getting these numbers from the end amount here from the rice table, over 0.85, which is the total amount of pressure at the end, right? And that's what the mole fraction is going to be equal to. Let's go ahead with O2. That's going to be 0.6 minus 0.45, again, 0.15 times 3 for 0.85. X of CO2 is equal to just 0.15 over 0.85. And then X of SO2, which is just these numbers. Again, I'm just getting these from the rice table up here. 2x times 15. Let me just draw this out so it's not too confusing for everyone. Over 0.85, right? And then when we finish solving for these equations, we get this is numbers going to be 0.294, 0.176, 0.176, then 0.353. So that's the end of the problem. Wasn't too hard, right, guys?